Hello folks, we're back with another episode. Last time we did the directional derivative and we saw that there was an easy way to calculate this directional derivative given the function. So let me just make a quick summary of what we did last time because we're going to work on that quick way, which is the gradient. Given a function f of x, y, okay, we wanted to find, this was d sub u f, right, was the derivative of f in the direction of the unit vector of u. Okay, and this was always going to be a unit vector. If it wasn't a unit vector, if they just gave us some other vector, we just divide by its length. Otherwise, it didn't make much sense. Okay, so we saw this last time. I cut up a QE for you guys to show how it will look like. And there was the limit definition, just like normal derivatives from Calc 1, which took a long time, but then we realized something. We had to make a definition, and we made the definition that gradient of f, we started doing this vector function. Okay, gradient of f was what? It was f sub x I plus f sub y j. Now, I want to be a little bit careful here, okay? So, for example, if we look at our old function, we had the example f of xy was equal to, I think we did x squared y, right? Now, so from here, we get that f of f sub x is just going to be 2xy, and f sub y is going to be just x squared, okay? So, gradient of f, what we call gradient of f, is going to be just going to be 2xy I plus x squared j. Now, this is not a vector, right? This is not a vector. This is a vector function. It's actually what you can call a vector field. It defines for x at each point in the plane. It defines a vector originating from that point. Okay, so it might look, you might see crazy things like this. It goes this way, it goes this way, it goes this way. Maybe it's here it goes this way, here it goes this way, here it's really large or something like that, okay? So each point is associated with some kind of vector, okay? Maybe it's the water flow on some crazy channel or something like that. But it's not itself as a vector. When does it become a vector? When does gradient become a vector? When you plug in a point. So this is the gradient. Gradient is not a vector, okay, not a vector, but the gradient at a point, gradient f evaluated, say, at a point p naught, is a vector, okay, is a vector. So if we were trying to say, for the above example, if we're trying to find gradient of f at, I don't know, 2, 1 or something like that, okay, you would get what? This would be just 4i plus 4j. Sorry, came out symmetric. Okay, what can you do? So that's a vector. Now, what did we learn last time? We stopped, I think, where we said d sub uf is just equal to the gradient of f dot product u. Okay? In other words, if we were talking about the point, the derivative at a given point, at the point p naught, you would evaluate the gradient at that point p naught, and use a unit vector. You can't plug in anything there, so this would be your answer. Okay, this would be a real number, right? It's the slope of a line. Real number. Okay. Okay, so I showed you guys the proof of that using the chain rule. That was a very neat application of the chain rule. Now I want to go on and develop some properties of it. Now, this guy, of course, because we're talking about the dot product, this is a vector, right? And this baby is a vector also. So, well, remember, if we have two vectors, uv, okay, well, the dot product u dot v, right, was, this was a real number. Again, what was it? It was the length of u times the length of v times cosine theta, where theta is the angle between these guys. Okay, so theta is the angle between these two vectors. Okay, so using that information, we can get something very nice, I believe, from this information. And what I'm going to think now is, let's look at du directional derivative in the direction of u, okay, of the function f. Well, we said that this was equal to gradient of f, okay, times u, okay. Now, at a point, let's give ourselves a point p naught. Let's give ourselves a point p naught, okay. Now, these are two vectors. So what do I know about the dot product of two vectors, right? That's going to be, I can just plug in the definition, and that's just going to be the length of gradient. So this is a vector now. P naught is a vector. Its length times length of u times cosine theta. Okay. Now u is unit. U is unit. So obviously, right, length of u is just 1. Okay, so we can just get rid of that. Okay. So this is very interesting. Then we can conclude the following. So let's skip the middle steps now. If we look at the directional derivative at p naught, well, then that's just going to be the size of the gradient f evaluated at p naught. Well, length of u was 1, so we don't care about that. That's just going to be cosine theta. Now, of course, the cosine theta is one of those trig functions that we love. Well, it's bounded, right? The maximum value is going to be 1, and the minimum value is going to be minus 1. So we can say that the directional derivative is always bounded by the absolute value. Okay, of gradient f, and it's bounded below by negative the absolute value of gradient of f evaluated at p naught. Okay, sorry. Okay, so basically we got these two things. Okay, so the absolute, it's always going to be bounded by gradient of f. Just the maximum value is just going to be gradient of f at that point, and the minimum value is negative the gradient of f. Now, in absolute value, of course. Having said that, when will this occur? This will occur when exactly theta is 0, i.e., when will it occur? It will be when u is parallel to gradient of f. Okay, and when will this happen? When will it have the lowest value? When they're in opposite directions, right? When u and gradient of f are in opposite directions. Directions. Okay. Okay. So this would be when, of course, theta is equal to pi radians. Everything is radians in here. So we can now make a summary, and we can use this information. Okay. So what does it mean for the gradient to be maximum? Okay, for the directional derivative. The directional derivative to be maximum. Well, directional derivative is maximum when you have when you're in the direction of the steepest increase, right? When the function increases most rapidly in that direction, okay? DUF is going to be max when it's going to be in the direction of steepest increase, most rapid increase. Okay, DUF is going to be minimum. Min in the direction of steepest decline. Okay, steepest decrease. So this said, we said this is going to be in the direction of the direction of the gradient of f at that point. This is going to be in the opposite direction. In the opposite direction of gradient of f. Okay, there's one thing we can conclude also. So when will there be no change in the function when the derivative is 0, right? Okay. So when will be the derivative 0? That's the question. Well, that's going to be 0. Again, we're talking about the dot product. The dot product of two vectors, right? Gradient of f evaluated p naught times the vector u will be 0 when u is perpendicular to gradient of f evaluated at that point. Of course, this assumes, assuming gradient of f can't be 0 at that point. If you have a 0 vector, right, everything is perpendicular to it. It doesn't make sense. It's not equal to 0. Okay. So how do you find the change in direction? How do you find the change in direction where steepest increase? Well, that's going to be in the direction of the gradient. Steepest decrease, okay, the most rapid decrease, that's going to be in the opposite direction. And there will be no change if you are perpendicular to it, okay? So I'd like to do an example about this, okay? It doesn't make much sense by itself. Let me give you a function. As an example. Let's look at this function. F of x comma y is this funky guy, cosine x, cosine y, okay? And let p naught be, let's say pi over 4 and pi over 4. Okay, so basically we're talking about 45 degrees and 45 degrees. Okay, so I want to find the steepest increase. Find the directions of steepest increase, decrease, and no change. Okay, no change in the function. Okay, also let's find the derivatives. Also find the value of the derivatives. So this will put everything we've done so far. It'll bring it all together in this example. Okay, so the first order of business that we got to do is we need to calculate these partials. We need to calculate fx and fy. Okay, so remember when we're talking about f sub x, we're treating everything that has y in it as a constant. So cosine y, that's just like 3, 5, minus 8 or something like that. It's just a constant number. I'm going to take the derivative of this, cosine x. Well, what was that? That was minus sine x. So we get minus sine x cosine y. Correct? And if we're talking about s of y, now I'm treating this guy as x. So it's going to be minus sine y. So I'll put the minus in here. Okay? Minus cosine x sine y. It's actually cosine x times minus sine y, but I'll just pull the minus in front. Okay. So now what do we know from these two guys? We've concluded that gradient of f is going to be minus sine x cosine y I plus minus cosine x sine y j. Okay? So obviously we need to now evaluate this at this point. So we're going to get gradient of f evaluated at this point p naught is going to be, let's plug in pi over 4, right? That's going to be square root 2 over 2, square root 2 over 2. So we're going to get 2 over 4, which is just like 1/2, okay? So we get minus 1/2 I, okay? Plus, let's plug it in here. we're going to get square root 2 over 2, square root 2 over 2. Again, that's 1/2, and there's a minus again. Okay? Minus 1/2 j. Okay, so this is the gradient vector evaluated at that point. Now, we want to find steepest increase in the direction of minus 1 over 2I minus 1 over 2j. Okay, but when we say, remember, when we're saying the direction, it's a vector that has length 1. This doesn't have length 1, right? So what we need to do is we need to take this guy and divide it by its length, right? So what is the length gonna be? So we have to turn it into a unit vector. We have minus 1 over 2I plus 1 over 2j, right? Times, over. We have the square root, square these, you have 1 over 4 plus 1 over 4, plus 1 over 4. So we basically have 1/2, okay? So we get minus 1/2 I plus 1/2 j. And on the bottom we get, this is going to be 1 over 2, so it's square root again. It's just 1 over square root 2, okay? So what do we get when you divide both terms? You get 1 over square root 2I plus, sorry, this wasn't plus. Sorry, this was minus. My bad. Sorry, guys. Folks, that was my bad. This is minus 1 over square root 2j. All right. So this would be the steepest increase, would be this direction. Okay. And what would be the value? The UF, okay, the UF evaluated at P naught. Well, what would be the value? It would be just gradient of f times this guy, right? What's gradient of f? So that's going to be minus 1/2, minus 1/2, minus 1/2. That was the gradient evaluated at that point, times minus 1 over square root 2 minus 1 over square root 2. Okay. So this is the dot product. And once we do this, we're going to get 1 over, so it's just going to be 1 over 2 square root 2 plus 1 over 2 square root 2. So I just have 1 over square root 2. Okay? So that's the direction of steepest increase. Now let's quickly do the same thing for direction of steepest decline. Steepest decrease is going to be in the opposite direction, opposite to gradient of f. Okay, so what would be, again, you got to be careful. Then we want 1/2 I minus 1/2 j. But again, this is not unit. So change it into unit, and you'll see. Well, plus. This is plus. Sorry. We get the exact same thing with the signs reversed, of course. We get 1 over square root 2I plus 1 over square root 2j. Okay? Then the derivative in that direction, okay, the smallest value of the derivative, okay, at P naught is going to be, this was the gradient times, this is the u, 1 over square root 2. Again, I'll just skip the steps because we're just redoing them. So that's just going to be now minus 1/2. Okay, it's exactly this guy with a minus sign. So that is something to keep in mind. If you calculate the steepest increase, you can just multiply it by a minus sign. And that's just going to give you the steepest decrease, right? Okay, so you don't have to do this work 2 times. I just did it once so that you can see it with your eyes, and you don't have to worry about it. All right, now so now let's talk about the direction of no change. When do we have no change? So when does the function not increase and not decrease? When does it change? In which direction does the function stay constant? Which direction does the function stay constant? Okay, which direction does it stay the constant? It's going to be perpendicular. It's got to be perpendicular. Perpendicular got to be perpendicular perp to gradient of f, which was what? Which was minus 1. What was it? Minus 1 over square root 2? Yeah, minus 1 over 2. Hold on, let's bring it back. It was minus 1 over 2, sorry. Minus 1 over 2 I minus 1 over 2 j. Okay, so here's a trick. If you're trying to calculate, this is just a linear algebra problem, right? It's the null space. So here's a trick. You can just make one of these, keep one of them as it is, and keep the other one, change the sign of the other one. So there's going to be two of them. Let's say v1 in the direction there's going to be, you can do two of them, minus 1 over 2I, but we want it to be unit, gotta be unit again. So I'm gonna, let's change this into a unit vector. Let's say the unit vector here is just going to be this, right? So v1 is, I'm going to keep the first coordinate and I'm just going to change the sign of the second coordinate. So I'm going to make it a plus 1 over square root 2j. And v2, there's two of them. I'm going to this time make this one, I'll change the sign. Okay, 1 over square root 2i. And I'll keep the sign same on here, 1 over square root 2j. Now, if you see, if once you multiply the gradient of f, v1, gradient of v2, they're both 0. So in these two directions, right, there's going to be two directions. One direction and exactly the opposite direction. There will be no change. Okay, so this was pretty sweet in terms of figuring out which way will the function increase most rapidly, which way will the function decrease most rapidly, and which way will there be no change. Now, this has been, so far, all algebraic, right? It hasn't given us much intuition, unfortunately. Now, I would like to prove a theorem for you guys, okay? And this is gonna kind of let us visualize what this gradient of f vector is, okay? What is it? What's going on? What is it physically, okay? So far, we haven't gotten it. Now, I think we're gonna do it. So what I'd like to do is, let's consider the gradient and level curves. So we saw level curves before. What's the relationship between gradient and level curves? Now, remember, in our last episode, we had this kiwi that I cut open to show you what a gradient was. Now, let's say, so the kiwi is gone. Sorry, I ate it already. So we have a lemon now. No more kiwis left in the house. So let's take a point here, okay? Let's take a point here. So you can see the point. Now, so it's standing up like this. The level curve through this point, we're keeping z, the height, constant. So the level curve, turn it around so you can see it, is just going to go across like this, right? It's just going to be this level curve, right? It's going to be roughly a circle, okay? So it's going to be like this circle right here, okay? It's going to be a circle. Okay, so what I'm going to show you is that the level curve is always, or the gradient is always perpendicular to the level curve at any given point, which is profound actually, okay? Which has profound implications. So you have these level curves. If I cut this, they will be all kind of circular. So at this height, whenever I calculate the gradient, I know what the gradient is. Gradient is going to be perpendicular to the level curve. It's going to be perpendicular to the level curve here, perpendicular to the level curve here. But why is that? Let's see that. Okay, so the summary is the gradient is perpendicular to the level curve. Okay, so all right. So let's say the level curve of the lemon, it was probably a circle, but let's take a funky level curve. Okay, let's say we had a function. Let's say we had a function f of xy, and this is the level curve f of xy equals c. Okay, some constant. Okay, at some constant height. Now, because it's a curve, right? It's a smooth curve. Hopefully, it's a smooth curve. We can write it as, let's find, because it's a curve, let's find the parameterization of it. Let's say we found the parameterization. We described it as r of t. Okay, r of t, smooth curve. So it was g of t I, let's say, plus h of t j. Okay, we describe it like that. So from here, this would be my x component. This would give me my y component, right? Then from f of xy equals c. So from f of xy equals c, remember this describes a curve now, the level curve. We get f of g of t, h of t, okay, equals c. All right. Now, let's do derivatives. Okay, so we're in the subject of derivatives. Let's do derivatives with respect to t. Remember, this goes back to our chain rule. We have this function f as variables of x and y, and they are themselves variables of a third function t. These were the intermediate variables. This was the free variable. So if I wanted to write df dt, right? That would be the same thing as, right, df dx times dx dt, right, plus df dy times dy dt. All right. Now let's clean this up. So if we were trying to write this as the product of two dot product of two vectors, right? This is just f sub x. So it would be just f sub x I plus f sub y j, okay, times the dot product of, what is it, dx dt I plus dy dt j. Right? Okay. So, all right, but this function f of xy was equal to a constant. Okay. So if you with df dt, well, df dt, I know that's got to be 0, right? Because the derivative of a constant with respect to t is going to be 0. All right. So what does this say? What does this say? It says this is the gradient vector. Great. This is the gradient vector. And this is the derivative of r, the parameterization. Okay. That's just r prime of t. Okay. So the gradient vector and dot r prime t, well, that's equal to 0. What does that mean? What does that mean? That means, of course, when will the dot product of two non-zero vectors will be 0? If they are perpendicular to each other, isn't it? Okay. So, but what is r prime? But what is r prime? R prime is the tangent to this level curve, right? If we're given a point P naught here, right? The tangent will be r prime t. And if this curve was rt, the tangent is of course going to be r prime t. So it says r prime t and the gradient have to be perpendicular. So this would be gradient of f. Okay? So they always got to be perpendicular. So you take any level curve on the lemma, okay, you always stay on the same curve. That means you got to head out, okay? This is the direction. The gradient is heading out perpendicular. And that makes perfect sense, doesn't it, if you think about it? So which way will be the steepest increase? Well, if you go up this way, right? But on the xy axis, if you look at the xy axis, it means you gotta go in the direction of the gradient, and the steepest decrease is gonna be in the opposite direction of the gradient, okay? So I guess the gradient is, sorry, my bad, gradient is heading in on this one. Okay, so now r prime, so this implies, of course, once we have that, sorry, you didn't see any of that. Oh boy, sorry, so let me go over this. I wrote this as this, and this was just r prime of t. So if that is 0, that means the gradient and the vector have to be, the gradient and the curve have to be perpendicular. So the gradient vector, and the curve have to be perpendicular, are perpendicular. In other words, the tangent vector, okay, the tangent vector, i.e. the tangent vector to the curve is perpendicular, is perp to gradient f. Okay, so that's pretty sweet. Now let me do a quick example. I want to do a few examples of this. Okay, of this. We'll start real nice and slow. So here is going to be our first example. I'll try not to go out of bounds this time. Let's find the tangent line to x squared plus y squared equals 4 to at -1 -2. Okay, now hold on. Why did we do this? You know, we could do this in Calc 1 also, right? You could try to solve for y, or you could do a parameterization. This turns out to be an ellipse, of course. So why are we doing multivariable calculus on a Calc 1 question? The reason is, actually, we're imagining that this is not equal to 2, but it's equal to z. It's a function of some sort, okay? It's a function of some sort. So this is going to be the level curve. It's going to be the level curve at the height 2. Okay, so I want to find the gradient and the tangent line. So this is going to be an ellipse, right? Actually, it's going to be much easier if we write this, or let's keep it like this. Okay, so it's going to be some sort of ellipse. The vertical is going to be bigger, so it's an ellipse like this. Okay, and -1, 2, we're probably somewhere around here, and the tangent line is going to be this, and the gradient is going to be perpendicular to. So this is the tangent, this is the grade, this is the normal. Okay, normal line, and which is the gradient. Okay, so let's do the math here. So I'm going to write f of x, y. I'm going to imagine this as the function x squared plus y squared over 4. Okay. So here, if we do the gradient of f, okay, that's easy now. It's going to be 2xi plus the 2's will cancel, y over 2, j. Okay, so the gradient of f evaluated at our point. What was the point? -1, -2. Just plug it in. We get minus 2i, and we get -2 minus a j. Okay. So our tangent line has, this is the gradient. Our tangent line has to be all those points which are perpendicular to this. Okay, so tangent line will be all those points, will be the set of points okay, perpendicular to the gradient of f. Okay. So, but how am I going to find the set of points perpendicular to, sorry, the camera is falling down. Perpendicular to the gradient of f. Okay, so how are we going to find all those points perpendicular to the gradient of f? Well, whatever it's, so we have our x naught, right? We have our x naught. Let's say, sorry, we drew it already here. X naught, let's say this is a point x, okay? So what do we know? This, if we see this as as x naught, this is x naught, y naught, and let's say this is the point xy. Sorry, let's put these as points. Okay, so what needs to be true is x minus x naught, right? That's a vector. X minus x naught times x minus x naught, sorry, comma, y minus y naught. That would be that vector. It would be this vector here. Okay, and that's, if that's going to be perpendicular to the gradient, the normal vector times gradient of f, evaluate that p naught, should be, the dot product should be 0, right? They are, because we said that they are perpendicular. All right. So what does that mean? When will they be 0? Well, let's do the dot product. Well, what will we have? That means minus 2 times x minus x naught. That was the gradient vector, right? Minus 2 times x minus x naught plus, sorry, minus y minus y naught is equal to 0. So that's a nice way. That's a nice way to find tangent lines to level curves. So the formula for a tangent line to a level curve f of xy equals c is, what is it going to be? It's going to be, we got to give the point at p naught equals x naught y naught is, what is it? It's very nice. It's going to be just f sub x minus x naught plus f sub y minus y naught, going to be equal to 0. Okay, so we get this nice sweet formula for tangent lines to, this is going to be TL, tangent line to a level curve. Okay, so we're almost done. Just bear with me. We have the tangent planes to go through, and then I'm going to do one more example so that you can see this in action. What about the tangent plane? Now, let's go back to my lemon, right? This whole idea of a directional derivative started because if we pick a point, let's say we pick this point on the lemon, right? The derivative was not well defined. We had to first of all give the direction. If I said, let's say this direction, then I would cut the lemon like this. If I said this direction, I would cut the lemon like this. If I said this direction, I would cut the lemon like this, right? So each direction on the paper, on the plane, gives me a way to cut this lemon. Now, because the tangent lines are not defined, but the tangent plane, so the tangent plane would be well defined. So if just watch my hand, the tangent plane would be well defined. So how would we calculate the tangent plane? How would we calculate the tangent plane? That's our next issue, okay? So let's ready our paper. Tangent plane. I mean, we've actually done it already, okay? Because how? Well, if we given a function f of x, y, z equals c, okay, equals c. Okay. Now, hold on a second. This is a function of 3 variables equals c. So So it's actually a four-dimensional object. It's like the level curve of the four-dimensional object, but the four-dimensional object, right, doesn't have a level curve. It has a level surface actually. Okay. So what's going to be tangent to this level surface? Well, it's not going to be a line because lines are not well defined to surfaces. It's going to be a tangent plane. Okay, so I think we're getting to this idea of the level surface. This is the level surface. It's not going to be because it's four-dimensional, it's not going to be a curve anymore. It's going to be a surface through through the point. Let's look at P naught. Okay. Through the point P naught is normal, is of course again going to be normal to a gradient of f evaluated at P naught. So again, what's got to be true then is that f sub x evaluated at P naught times x minus x naught plus f sub y evaluated at P naught y minus y naught plus f sub z minus z naught. Okay, this has got to be 0. Well, okay, so I can imagine you are complaining. You're like, we're not done with just functions of 2 variables. Why are you doing a function of 3 variable? Because now we're going to see from this is going to imply something very sweet. If we have a function z equals f of xy, right? Okay. If I define a function z equals f of xy, well, I can say this is exactly the same thing as f of xy minus z equals 0. Now I can see this as a new function of 3 variables. Okay. Then the tangent plane. This is the tangent plane. Sorry, I forgot to label this tangent plane. So from the above, we can get the tangent plane. Then the tangent plane, sorry, bad spelling there. Tangent plane is going to be what? F of x times x minus x naught. Sorry, evaluated at P naught, of course. Plus f of y evaluated at P naught, y minus y naught. All right. But now z, hold on, fz, well, it was just minus z, so that's just minus 1, right? There's nothing to it. Fz is just minus 1. F sub z is just minus 1, so minus y minus y naught. Sorry, very bad. Minus z naught is equal to 0, okay? So because it was just, we know what it is, it's just minus 1z, the derivative of with respect to z is just minus 1, okay? So that will give us the tangent plane. Now, figuring out the gradient, okay, figuring out the normal line is very easy. Normal line is going to be in the direction of course, the gradient. So what is it going to be? So you just need to figure out, so it's going to start from x naught because it's normal, it's going through that. And so it's parameterize it. How are you parameterizing it? Well, you're going to look at the x component of the gradient, okay, times, let's say, t, okay, and y component is going to be y naught plus f sub y evaluated at P naught times t, and z component is going to be z naught plus f sub z evaluated P naught times t. Alright, of course t, because these are lines, t is between negative infinity and infinity. Okay, so that was it. That's what all we're going to do. Let's do a couple of examples, maybe 1 or 2 examples, and finish this lecture. So I picked, I have an example here. Let's calculate. Let's find something from the notes. let's look at this function. Okay, let z be equal to 1 over x squared plus y squared, and p naught is 1, 1, 1/2. Okay, so I want to find the tangent plane and the normal line. Find tangent plane, plane, and normal line. All right. So at this point, of course. So what was it? What was it? So what we kind of thought of this as it's going to be 0 equals 1 over x squared plus y squared minus z. Okay. So the thing here is the tangent plane. Tangent plane is going to be what? F sub x evaluated p naught times, it's going to be x minus x naught is just x minus 1, right? Plus f sub y evaluated at p naught times y minus 1. And it's just going to be minus 1 because that's the derivative here, right? F sub z is just minus 1 again. It's always minus 1 when you have a function of two variables. Z minus 1/2 equals 0. Okay, so let's do this actually. So what is f sub x? Let's calculate f sub x. F sub x is going to be, sorry, I went out of bounds again. F sub x, okay, so we have 1 over x squared plus y squared. Remember, when I'm doing f sub x, y is like a constant for me, okay? So I'm going to treat it as just a number, just a number. So what is it going to be? This is actually is x squared to the x squared, y squared. Actually, let me just write it like this so that you guys don't get confused. It's actually x squared, y squared to the minus 1, right? And sorry, I got a battery warning. All right, so we're good. We should be good. Okay, so it's to the minus 1. So what are we going to get? We're going to get minus 1 x squared plus y squared to the minus 2, okay, times derivative of the inside by the chain rule is going to be 2x. So what we get is minus 2x over x squared plus y squared, the whole thing squared, okay. So we were going to evaluate this at the point 1, 1, 1, 1, 1/2. Well, we just care about the 1, 1 part of it, right? There's no z here. 1, 1, 1/2. Plug in 1, you get minus 2, 1, 1. We'll get again 2. So this is just minus 1. No, it's not. Sorry, 1 minus 2. This will be 1, 1, 2, 4. So it's minus 1/2. My bad. Minus 1/2. Right. So let's do the same thing with f sub y. So we can do it in our head now. It's the same thing. It's just symmetric. Minus 2y over x squared plus y squared. The whole thing squared. Evaluated again 1, 1, 1/2. We said, right? So we cared only that we don't care about the 1/2 part here, right? It's again going to be minus 1/2. Okay. So great. So we have our tangent plane. So let me get a second paper. I'll try to keep them together so we can continue. Sorry about that. Ran out of space. All right. So we are here. We are right about here. So from here we get tangent plane is going to be who? It's going to be minus 1/2 times x minus 1 minus 1/2 times y minus 1 and minus z minus 1/2 equals 0. That's going to be our tangent plane. What about the normal line? Normal line, it's very easy to read off here. It's going to be x is equal to, well, x naught was 1 minus 1/2 t. Y, that was also 1 minus again 1/2 t. Okay. And z is going to be, what was it, 1/2 minus, It's just 1 minus the t. Okay, so that would be our line. Of course, here t is again between negative infinity and infinity. Okay, so that's an example of this just applied. Let's do a hard one, a much harder one. So let's do something a little harder. Example. We want to find the parametric equation. Parametric equation of the line tangent to the curve of intersection of the following surfaces at the point P naught, and I'll give you the point square 2, 4. Okay. Right. So what are the first surface? My first surface is going to be x squared plus y squared is going to be 4. Okay. And the second surface is going to be x squared plus y squared minus z is equal to 0. Okay, so I got these two surfaces. Now let's think about these two surfaces. This guy is a cylinder, right? It says that it says that level curves are always circles with radius 2, so it's just a cylinder. Okay, and the other one is just a paraboloid. Okay, or paraboloid opening upwards, because this is the same thing as, remember we saw this before, this is the same thing as the x squared plus y squared. This is a paraboloid. So what we got here is we have a paraboloid like this, okay, like this, and it's being intersected with a cylinder like this. Okay, so sorry for the horrible drawing, my bad. So the curve of intersection is going to be this guy, right? The curve of intersection is going to be this guy. So immediately we know that the curve of intersection is basically going to be a circle, right? It could have been an ellipse, but in this case it's always going to be a circle, because hey, it's the level curves of the cylinders are always the same. All right, so very good. Now let's find the gradients of f. I'm going to call this f. I'm going to call this g. Let's find the gradients of f and gradients of g. Okay, so what we have is, I'm going to write these as functions of 3 variables. So from here, x squared plus y squared equals 4. We're going to write this as x squared plus y squared plus minus y squared minus 4 is equal to 0. Okay, so we see this as a level curve. And this guy, x squared plus y squared minus z, it was this guy, okay, equals 0. Well, it's gonna stay by itself. Okay, so here let's call this guy, I'm gonna call this guy f, I'm gonna call this guy g. Okay, now this is a function of 3 variables. Okay, so it's the level surface at 0, at the height 0, and this is a function of 3 variables again. It's just there's no z in it. Okay, so the z derivative is just 0. So let's calculate gradient of f. Gradient of f is going to be, the gradient f was this guy. Okay, what is it going to be? It's going to be 2x, 2y, and there is no z, so that's just 0, right? And what is gradient of g? Well, let's do it's going to be again 2x, 2y, But there is a z in this guy. That guy is just going to be minus 1. Derivative of z with respect to that one is minus 1. So in other words, if we write down the vector notation of these guys, this is going to be 2xi plus 2yj, sorry, 2yj plus 0k, okay? And this is the same thing as 2xi plus 2yj plus minus a k. Okay, from here, again, when we start a problem, if we set these guys equal, right? If we said when will the curve intersection, we need to have x squared plus y squared, okay? And this was this. That's supposed to be equal to 4, and at the same time it's supposed to be equal to z, right? Okay, so what is this? This is just a circle. So the curve is just a circle with radius 2. So, okay, curve of intersection. This guy, I drew it sideways. Curve of intersection. Okay, so the question here is, I want to calculate where was our point. What was our point? Yeah, square root 2, square root 2. Okay, square root 2, square root 2. So we're here. Sorry, we're not there. We're somewhere else. Because x is going to be here, y is going to be here. So square root 2, square root 2. The positive ones is going to be here somewhere. Okay, so we're talking about this tangent here. Okay, we want to find this tangent plane, this tangent plane, the tangent line to this curve. Okay, so how am I going to find that? Well, if it's going to be tangent to the curve, it's going to be perpendicular to both gradient of f and both gradient of g, right? The tangent line is going to be perpendicular to the gradient of f, and at the same time the tangent line is going to be perpendicular to the gradient of g. So I need to evaluate these guys at this point. Let's evaluate these guys. Gradient of f evaluated, our point was square root 2, 4. Let's evaluate it. What do we get? We get 2 square root 2, 2 square root 2, and 2 square root 2, and basically nothing, 0. We get this guy. Okay, and finally, if we evaluate gradient of g at square root 2, square root 2, 4, we get, again, we're going to get 2 square root 2, 2 square root 2, but this time we're going to get a minus 4. Okay, so we got to find the tangent line to the curve. Tangent line to the curve, the tangent line to the curve of intersection, the curve of intersection is going to be perpendicular to both gradient of f and gradient of g, right? Okay, so let's remember, how do we find a third vector that's perpendicular to two vectors? Well, we have to do the cross product. Okay, so let's do the cross product. Gradient of f evaluate at p naught cross gradient of g evaluate at p naught. Okay, so what is it going to be? How did we do this? Remember, it was the determinant of this matrix. The first one was 2 square root 2, 2 square root 2, 0, 2 square root 2, 2 square root 2, 2 square root 2, minus 4, okay? And if you do this, not minus 4, this was minus 4, my bad, this is just minus 1, right? It's just minus k, it's minus 1. Sorry, my bad. My mind wanted this minus 4. It's just derivative. It's coming from this guy, right? Minus 1. It's just minus 1. Okay. So if you do this, it comes out. Well, I did it. You can check it at home. No surprise. It comes out 2 square root 2 I plus 2 square root 2 j plus 0k. This is going to be minus this is going to be plus, because that way it's going to be perpendicular to both of them, right? If we switch this, it's because it's 0, it's going to make multiple dot product of this guy will be 0 also. Okay, so we can then parameterize our tangent line. Tangent line will be what? We can parameterize it. X is going to be, the point was, what was our point? Our point was square 2 plus, minus 2 square 2 t. Y, that was also square 2. The initial point was square 2 square 2, 4. Plus 2 square 2 t. And finally z, well, it's just going to be the point itself. Is always going to be, what was it, 4 plus 0 t. Again, t is between minus infinity and infinity. Well, I hope you found that helpful. Sorry, let's do this. I found that you found that helpful. So this idea of the gradient as a vector perpendicular to the level curves and level surfaces gets us a lot of mileage, really. You can calculate the tangent lines, tangent planes, and all that good stuff. And I hope to see you next time. Next time when we do something else. I think we're going to do maximums and minimums. Take care. Bye-bye.